So this video we are going to see AVL tree. So we have seen binary search tree. So in binary search tree, two properties are there. The structure property is that every node can have a maximum of two child nodes, and the value property, the search property, is every node should have a greater value than all the values at its left subtree, and it should be having lesser value than all the values at its right subtree. So why are we having this condition is, if I'm searching for a value from the root, if I start my search, based on the comparison, I can either go to the left subtree or to the right subtree. So the search can be efficient. But the problem is, if the binary search tree is skewed towards left or right, then the number of comparisons to be made will be more. Again, the search properties advantage will be lost. So we are moving to the balanced search trees. So in the balanced search tree, here we are going to discuss on AVL tree. The other balanced trees available are red black tree, 2 3 tree, and B trees. So in AVL tree, the property is it has to be a binary search tree, and uh, so along with the binary search tree condition, we have the height condition as well. So for every node, we will be calculating the balance factor, and the balance factor of every node should be uh, 0 1 or minus 1. Okay, so that is the main condition we have here, and the balance factor is, it is the difference between the heights of the left and right subtree. Okay, so that should be at most 1. So how usually we calculate balance factor is, height of the left subtree minus height of the right subtree. Okay, this is what the uh, formula we calculate the balance factor. So for every node in the tree, the balance factor should be either 0 or 1 or minus 1. Okay. If it is becoming 2 or minus 2, then that tree has to be balanced. So for balancing the tree, we have some rotations based on the insertion that we are making. We are having different kinds of rotations. So if it is 0, means if the balance factor of all the nodes are 0, means every node, either every node is a leaf node, or all the nodes are having equally the height of the left and right subtree are equal. If the balance factor is becoming 1, means the left is heavier than the right side, and if it is minus 1, right is heavier than the left side. Okay. So the example is shown here. If you take this tree, first of all, it is a binary search tree. Okay, it is a binary search tree. If you take 10, 10 is greater than all the values in the left side, and it is less than all the values at the right side. And if you take 5, 5 is greater than 4 and 2, and it is less than 7 and 8. Similarly, if you take 4, it is greater than 2, and right side is empty. And also, if we check the balance factor, how to calculate the balance factor? The height of the left minus the height of the right. Otherwise, we can calculate it as the number of levels in the left subtree minus the number of levels in the right subtree as well. If you check for leaf nodes, so for leaf nodes, the left side is empty and the right side is also empty. So there is no level at all. 0 level, 0 level, no level. Hence, the balance factor will be 0 here. And if you take 4, 4, the left side we are having 1 level, and the right side nothing. Okay, the number of levels in the left side is 1 level, and here it is 0. No level is available here. So we are having 1 minus 0, hence the balance factor is 1. Okay, and you can calculate using the height as well. If you take the left subtree height, here I'm having only one node. When there is only one node, there is no edge at all, then the height will be 0. And here none, the right subtree of 4 is none, so the height is minus 1. Okay, so for an empty tree, the height we are taking is minus 1. Hence, the balance factor will be the height of the left, which is 0, minus the height of the right, which is minus 1. Hence, we are getting the value as 1. Okay. Otherwise, we can simply understand that the left side is having heavy than the right side. Hence, it is having positive 1. Okay. And if we take 7, the left side, there is no level at all. It is 0, 0 number of levels. And at the right side, I'm having only 1 level. So 0 minus 1, we are having the balance factor as minus 1. If we take 5, 5, the left subtree we are having is two levels, 4 and 2. 4 is at one level and 2 is at the next level. Similarly, at the right side, I'm having two levels, 7 and 8. And hence 2 minus 2, we are getting the balance factor as 0. If we take 20, the left subtree is having one level and the right subtree is having none. Hence, the number of levels here is 0. So 1 minus 0, we're having the balance factor is 1. And if you take 10, the left subtree we are having is three levels we are having. So 3, and here if you take the number of levels in the left subtree is 3 levels. 5 is at one level, 4 and 7 are at level next level, and we are having the next is 2. So we are having 3 levels, and at the right side we are having 2 levels, 20 and 12. So 3 minus 2, we are getting the value as 1. Okay. And hence the values, all the balance factors are either 0, 1 or minus 1. Hence it is an AVL tree. Instead, if you check here in this tree, since there is no 12 here, for 20 the balance factor, for all the leaf nodes the balance factor will be 0. Hence it is fine. Now when we take for 10, the left subtree is having three levels. 5 is at one level, 4 and 7 are at another level, and 2 and 8 are at another level. So 3 levels we are having. So 3 minus, and the right subtree we are having just one level. So 3 minus 1, we are getting the balance factor as 2. The formal formula for calculating balance factor is height only, height of the left minus height of the right, but it is easy to use the number of levels what we have to have the calculation of balance factor. Okay, fine. When I'm constructing the tree, it is not that always it will be balanced based on the value what I'm inserting. It may become unbalanced. So in that case, to make it balanced, we have to go with some rotations. So if you take this tree, here initially we were having 3 and then 2. When 1 is inserted, the balance factor of 3 is becoming 2, which is not allowed in the AVL tree. So we have to make it balanced. So for that case, what do we do? If I'm inserting this here, in this node is getting unbalanced, it is getting the balance factor as 2. So this we are calling as pivot node. Okay, so with respect to the pivot node, where I made the insertion, that I have to take. So where is it made? In its left subtree and its left. So left of left, the insertion is made. If the insertion is made at left of left, to balance it, we need to go for one single right rotation. So we have to rotate towards right side. So when I'm rotating towards right, what will happen? The child 2 will be occupying the position of parent, and the parent will be depromoted to the position of child. So we are getting this. And now if we check the balance factors, it is becoming 0. So this is for example for a single rotation. Instead, if I have the insertion like this, okay, initially I had 3 and then I inserted 1, and then the insertion is done here as 2. So in this case, 2 balance factor is 0, for 1 the balance factor is minus 1, but when we take the balance factor for 3, it is becoming 2. So when it is done, this is the pivot node. Okay, this is a pivot node. With respect to the pivot, the insertion is done at left subtree and then right subtree. Okay, from the pivot node, the next two directions we have to look at. Okay, left left or left right, or it can be right right or right left. So here it is made as left and then right. So here we have to go for two rotations. The first rotation will be with respect to 1, it will be rotated towards the left direction, and then it will be rotated towards the right direction. Hence it is referred as LR rotation, first left and then right, if the insertion is made in left right. Okay, and since we are going for two rotations, it is referred as double. Okay, so when we are doing the first rotation with respect to this, how will it be becoming is 3, and then 2 will come to the position of 1, and 1 will come to the child of 2. So first the left rotation is completed. Then here I have to do the right rotation. As a result of this, we got this tree. Okay. So this is a simple example of the rotation. If I'm having a general case, then how the rotation will be is, okay. So here we are having R, the parent node. Okay. Then from R, I'm having the left child C, and from C, uh, so R's left side and that child's left side, the insertion is done here. Okay. Here the insertion is made. So till the insertion, the tree was balanced. Because of this insertion, its balance factor is becoming 2. Before it is getting inserted, this was having the balance factor is 1, and now due to this insertion, now it is becoming 2. If it is, then we are going for right rotation. When the insertion is done at the left of left, we are going for right rotation. So how it is done? We are making a right rotation here. So child is taken to the position of parent, and parent comes to the right position of the child, and the other nodes will be there. And if you notice this T2, okay, since C is becoming parent and R is becoming its right child, the T2 is taken to the left child of R. Okay. So this is how the single R rotation is done. Similarly, we'll be having the single left rotation also. That will be the mirror image of the same single R rotation. Okay. Single left rotation will be the mirror image of a single R rotation. So this is generally case. Similarly, for the double rotation, the LR rotation, how it is done. So this is a parent we are having. The parent's left side that we are taking as the child, and the next level right side. And it is not that the next insertion has to be immediately here. It can be anywhere in the subtree of this grandchild. Okay, and it can be either here or here with T2 or T3, the left or right of the G. But we take only the two next immediate directions with respect to the pivot node. Okay, this R is representing the pivot node. So if it is after the double rotations, the result will be the G is taking the position of R. So G comes here. Okay, and R is taken to the right side of G. So we are having this here, and this C will be becoming the left child of G. And if, now R is becoming right and C is becoming the left. So what will happen to this particular trees, T2 and T3? So T2 will be taking the right position of C, and T3 will be taking the left position of R. Okay, because of the binary search tree property. Okay, for every node, the left should be lesser and the right should be greater, right? So to satisfy that property also, this assignment is done. Okay, so with this, let us have some example of inserting and rotating. So the insertion will be with the as how we are doing in the binary search tree. Initially, I'm having 5, so 5 will be becoming the root node. Then I'm having 6. So since 6 is greater than 5, 6 will be inserted as the right child of 5. When I am inserting, always it is inserted as the leaf node only. So the balance factor will be 0. And for 5, the right side is becoming heavy, so the balance factor will be -1. Left side no level and right side 1 level, so 0 minus 1 minus 1. 6 is inserted. Next time having 8, so 8 is greater than 6, so it is inserted as the right of 6. Now for 8, the balance factor is 0, and for 6, the balance factor will be -1, and for 5, left side 0 level and right side 2 levels. Hence 0 minus 2, the balance factor will be -2. So now the balance factor is becoming -2. So this is the pivot node. This is the pivot node. So with respect to the pivot, I have to check where I inserted the new value. So where I inserted, at the right of right, I inserted. So if it is right of right, it is the mirror image of the single right rotation. So I have to rotate towards left. So the result will be, when I'm rotating towards left, the 6 will occupy. So this is my pivot node in the general image. If I compare, this is my R, and this is child and this is grandchild. Okay, so when we are rotating, what will happen? The child will become the parent, and the parent will become the left child of the child node, and the grandchild will be remaining the same age. Now, if we calculate the balance factors, everything will be having 0. Now, let us insert 3. So, 3 is lesser than 5. So, it is inserted here. Its balance factor is 0. And 5's balance factor will be 1. And 6 balance factor will be 1. And 8 will be 0 itself. Okay, how 6 is getting the balance factor as 1? The left side I'm having 2 levels, 5 and 3. And the right side 1 level, 8. So, 2 minus 1, we are having 1. Fine, and it's still balanced because all the balance factors are within the limit. Then I'm inserting 2. 2 is lesser than 3, so it is inserted as the left child of 3. So what happened? Now this balance factor will be 0, and for 3 the balance factor will be 1. 1, since the left side level is more, and for 5 the left side level is 2 times more than the right side, hence it is 2. And since once I get a node which is having its balance factor as 2 or minus 2, I stop there. You need not go to the upper level and change it. So this is the pivot node. Now with respect to the pivot, the insertion is done at the left of left. If it is left of left, I have to rotate towards right. Okay. So this is my C, this is R, and this is grandchild. So only here the rotation happens. So 6 and 8 will not be disturbed. Okay, only here in the left side of 6 will be having the rotation. So this 3 will come to the position of parent, C will take the position of R, and R will go to the right side, and 2 will be remaining as the same position, the left child of 3. And now the balance factors here are 0, and there is no change in the other levels. Only with respect to the pivot, the rotation has happened. So only with respect to them, the balance factors will be updated, and the others will be the same. Fine, 2 is done. Next we have to insert 4, and 4 is less than 6, greater than 3, and less than 5. So it is inserted here. Now the balance factors will be, for 4 the balance factor is 0, and for 5 left side level is 1 more than the right, and for 3 right side level is 1 more than the left, hence minus 1, and for 6 left side I'm having 3 levels. 3 is at 1 level, 2, 5, then 4. So 3 levels we are having. So 3, and the right side I'm having only 1 level. So 3 minus 1, we are having the balance factor is 2. So its balance factor is becoming 2. This is the pivot node. Okay. Now with respect to this 6, we have to make the rotation. Now here with respect to the pivot node where the insertion is done, this is the insertion we made. So it is done at the left side, right side. Okay, left to right, the insertion is done. Then we have to go for 2 rotations. If I'm taking this as R, this is C, and this is G. If you remember the general format of the double rotation, okay, if you see here what happens, the G is taking the R's position, okay, and the parent will become the left one child, and the grandparent will become the other side child. So the similar rotation we have to do here. So what will happen? This G will go to the position of R. So 5 will take the position of R. This G will be coming here. G will be taken here. And here we'll be having C. C is 3. And on the right side we'll be having R. R is 6. And R is already having 8. And 3 is already having 2. Okay. And now 5 was having 4 as at its left side. Now this will be assigned to the C's right child. So when I'm having T2 and T3 for the G, T2 will be taken as the right side of the C, and T3 will be taken as the left side of R. Since T3 is empty, R will not be having any new left side, but C will be taking this T2. So we will be having 4 here. Okay. So now if we calculate the balance factors, this will be 0. For 6, it will be -1. And for 5, it is 0 because both the sides are having 2 levels. And C will be having 0, 0, 0. Now the balance factors, all the balance factors are zeros are -1. Hence it is balanced. Now when we insert 7, 7 is greater than 5 and 6 but less than 8. So it is inserted at the left side of 8. So its balance factor will be 0. And for 8 the balance factor will become 1, and for 6 the balance factor will be becoming -2 because the right side I'm having 2 levels. Hence 6 is becoming the pivot node. So now with respect to the pivot node 6, we have to make the rotation. So this is the pivot node, which means this will be R, this is C, and this is G. And here we have done the insertion at right, left. So the mirror image of the previous rotation. So other sides will not be disturbed now. Okay. So 5 will be in the same position. Only from here we will be having the alterations. The others will be the same. So 3, 2, and 4. So they are having 0, 0. And here we will be having the rotation. So what will happen? This G will be taking the position of R. In double rotation, grandchild will be coming to the position of its grandparent. So 7 will be taken to this level, and this C, the immediate parent, that will be in the right side, and this grandparent will be taking the left position, 6. Since there is no left and right side, T2 and T3 are not here, we are not getting any more left or right for the 6 and 8. So now the balance factors are 0. Okay. So this is how the rotations are done to balance the tree after the normal insertion in the binary search tree. Okay. Uh, so we'll take another example. Okay. So here, if you take this tree, the balance factors of 3 is 0, and for 2 it is -1, and for 5 the balance factor is 1. Okay, and for 9 the balance factor is 0. Okay, and for 10 the balance factor is 1, 2, 3, and here also 1, 2, 3, 3 levels we are having, hence it is having 0. And for 15 the left side 1 level and the right side we are having 2 levels, so the balance factor will be -1, and here it is 0, 0, 0. The other one printed is representing its height. Okay. uh, the blue printed values are representing the height of the particular nodes from its bottom level. What is the height they are having? Okay. 3 is at 0 height, and 2 is at height 1, and 5 is at height 2. So heights are mentioned so that you can easily calculate the balance factor. So for 10, if you have to calculate the balance factor, left side's height 2 minus right side's height, hence we are getting 0. And for 15, the left side height is 0 and the right side height is 1. Here you are having the height as right. So 0 minus 1, we are getting the value as -1. So using the height, the value is the balance factor is calculated. Okay, fine. And uh, now we are going to insert the value 33. 33 is greater than 10, greater than 15, and greater than 20, and greater than 30. So this has to be inserted at the right of 30. Okay. So now the balance factor of 33 will be 0, and for 30 it will be -1, and for 20 it will be -1, and for 15 it will be becoming minus 2. Okay, because for 15 the left subtree height is number of levels is 1, and the right side we are having 3 levels, hence it is becoming minus 2. Now this is my pivot node. Okay, now with respect to the pivot node where the insertion is done, so that has to be found. So with respect to the pivot node, the insertion is done at the right sides, right. So right of right, the insertion is done. Hence, we have to do a single left rotation. So single left rotation has to be done. Okay. So if I'm making the single left rotation, this is the pivot node. So only 20 and 15 that will be altering. The rest will be the same. So 10, 5. The others will not be disturbed. 5, 2, then 3, and here we are having 9. And here the change will be, the rotation is done here, which means 20 will be taken to this 15's position and 15 will be coming to the left side of 20. So 20 and left side 15, and 15's left already is 12, and 20's right side will be having 30, and 30 is having 33. Now what will happen to the 70? Since 20 has taken 15 as its left child, the 17 will be becoming the right child of 15. So 17 will be taking the right of 15. Okay, now the balance factors are 0, and here it will be minus 1, and here it is 0. And the other balance factors will be the same as earlier. Okay. So it's not that in a simple tree how we can rotate anywhere, however bigger the tree is, wherever we are doing the insertion, we need to update the balance factors towards the root node. And in the path, if any node's balance factor is becoming 2 or minus 2, immediately we have to work on it and it has to be rotated. So with respect to the pivot, we have to check the immediate 2 levels direction where it is done. Based on that, if the direction is unidirection, left left or right right, then we'll be having a single rotation. If it is left right or right left, then double rotation is done. Right now, similarly here, we are inserting 18 into this. When 18 is inserted, 18 is here, comes here. Okay, so the balance factors will be, here it is 0, and here it will be minus 1, and here it is 0, and for 20 the balance factor will be 1, and for 15 the balance factor will be minus 2, because the right side 3 levels, left side 1 level. So 1 minus 3, we are getting minus 2. So now with respect to this pivot node, we have to make the rotation. So the rotation we have to check by either single or double. In the right side's left child, we are having the insertion. So we have to, since we are having alternate directions, right and left, we have to go for 2 rotations. This is in general, with the general case representation, it is R, and this is C, and this is G. So when I'm doing the double rotation, G will occupy the position of R. So we'll be getting 17 in the position of 15, and 15 will go to the left side of 17, and 20 will take the right position of 17, and they will be having 12 here, and the 20 was already having 30 here. Now this 18, the right side of 17, that will be taken to the left of 20, and the other side will be the same as earlier, 10, 5, 2, 3, and 9. Okay, so we have made the rotations only here. Okay. So this is what the AVL tree is. A chart, it should be a binary search tree with the balance factor 0, minus 1 or 1. When it is becoming 2 or minus 2, based on the direction where it is inserted, with respect to the pivot, we have to decide the rotation and make it balanced.